So we have with us here Paul Asmuss from DAISY. So shall we start? Just tell us briefly the subject that you addressed in your talk.
I was talking about Higgs physics, basically, or mainly as analyzed, or as, the analyses performed at the two general purpose experiments at the LHC at CERN, namely ATLAS and CMS. And the Higgs particle, or the Higgs boson, is is the most recently discovered elementary particle, and is one of the key ingredients of the standard model of particle physics. So there are a huge amount of analyses targeting that particle, since, well, it's recently discovered, or rather recently discovered, and also there are several theories beyond the standard model trying to explain things that we see but don't quite understand yet. And several of these theories predict that either properties of the particle that we already discovered would differ from the standard model prediction, or would be similar particles. So there's a wide array of studies that are performed right now.
Okay. You have previous experience from Corfu. It's the first time you're taking part, and your opinion on the whole
work.
It
was the first time. Yeah, it was the first time, and I would have loved to come in person, but circumstances prevented that, unfortunately. But I was very glad that it was possible to attend via Zoom, at least.
And your idea about the whole workshop, your talk was in?
I liked it quite a lot. It was more theory focused than I previously thought. So, I mean, as an experimental physicist, I'm used to talk on conferences which basically just focused on very similar analyses. And I liked a lot that there was a wide array of topics. And I also really liked that they were separated by days. So you could choose to really focus on one topic on each day. That was very nice.
And your suggestion to new scientists, young scientists starting research?
So, yeah, I mean, there will always, of course, be bumps and roadblocks and everything, but it's definitely worth it. It's definitely worth to hang in there. And even if things might be a bit tedious from time to time, it's really an amazing feeling to be in exchange with some of the brightest people that there are, and to really contribute to sometimes groundbreaking discoveries and really a new understanding of everything.
Good. Okay. Thank you very much for this brief interview.
Okay, great. So I guess you also can see the slides in full screen. And then thank you very much for giving me the opportunity to present today the Higgs studies at both ATLAS and CMS. And so as a pre-remark, let's briefly talk about the standard model Higgs boson and how it was discovered. So, I mean, you are most likely aware that the standard model of particle physics is remarkably successful in both describing and predicting experimental results, and it was completed by the discovery of the Higgs boson in 2012. On the right-hand side, you see one of the two discovery channels, the diphoton channel, with the full run-2 ATLAS dataset, and you see why this channel is so liked, because you have a rather small background and this nice and clear Higgs peak above that. So far, the main production and decay modes of the Higgs boson have been observed, and we have, since the discovery, entered the era of precision measurements, for example, for the Higgs potential and targeting rare decays. Despite the strong success of the standard model, there is evidence that there must be physics beyond the standard model, BSM physics. For example, in the standard model, we don't have an explanation for neutrino masses, and there is no candidate particle for dark matter. So today I'm going to give an overview on recently published ATLAS and CMS results, targeting standard model and BSM physics alike, and all of these analyses are based on the full LHC run-2 dataset. So as I mentioned, I will also cover BSM physics, and for many BSM processes, the Higgs boson or Higgs bosons play a crucial role. For example, there can be additional Higgs bosons in enlarged Higgs sectors. There can be invisible decays of the Higgs boson, for example, to dark matter candidates, and there can be contradicting properties of the 125 GeV boson, contradicting the standard model predictions, for example, CP violation or changed cross sections and branching fractions. With this analysis, the total proton to Higgs to tau-tau cross section can be measured, and the result is consistent with the standard model prediction within uncertainties. And it is also measured per production mode, which you see here on the top left, as well as the combination on the bottom with respect to the standard model prediction. And the overall compatibility with the standard model is 88%. With this result, also the observation of the vector boson fusion production mode with a significance of 5.3 sigma can be constituted, as well as evidence for the gluon-gluon fusion with about 4 sigma. The cross-sections are also measured in terms of the reduced set of bins of the stage 1.2 of the STXS, showing good precision up to 24% in this bin here in the VH and VBF production mode with a large digit mass. And this is as well in agreement with the standard model predictions. So from the standard model going to rare decays of the Higgs boson, this search here targets invisible decays of the Higgs boson, where the invisible decay products could also target a dark matter candidate being the mediator. And the search for weakly interacting massive particles, WIMPs, indicated as chi in these Feynman diagrams here, relies on the associated production with Z boson to search for missing transverse energy. Furthermore, the Z boson is required to decay leptonically for a clean signature. Since dark matter must be massive, there's a strong argument to be made to look for it in interactions with the Higgs sector. And in this analysis, there are several benchmark models targeted. First, the decay of the standard model like Higgs boson. Second, a simplified S-channel dark matter production, for example, here. And third, 2x doublet model with additional pseudoscalar models, so here and here on the right. The interpretation of the limits from the first two of these are then compared with direct dark matter detection experiments. So dominant background contributions for this search originate from vector boson production, as well as some non-resonant WW or TT bar contributions. And then there are smaller contributions that are labeled other. In the plot here on the right-hand side, this other is not listed because it's negligible in the signal region. So the background prediction is compared to, the data is compared to the background prediction and the signal hypothesis in a simultaneous fit of the signal region, as you see here, which you see here on the right, and control regions. And the Higgs to invisible sensitivity is increased by using a BDT, a boosted decision tree, providing one single output variable. And this is used in the EMU control region, as well as the signal region, which is shown in the plot for the final likelihood. And you see that the signal hypothesis the contribution is indeed increased with increasing BDT score. So far, the data is in good agreement with the expectation, and the best fit constrains the branching fraction of the Higgs to invisible to be below 18%, which is also the expectation. And the improvements made in this new analysis lead to expected limits, so sensitivities, 45% better than the projection of previous techniques scaled to the full run-2 luminosity. So this is quite the huge achievement. And these results can also be transferred using the Higgs portal model to compare with direct dark matter detection experiments, which you see in red and blue here in the plot on the bottom right. And you see that it's quite compatible with direct searches. The next big block I'm going to talk about is the search for di-Higgs production. Today, I'm going to focus on recent results of the searches in the 4B and BB tau tau final states, referenced here again on the top right. There are, however, lots of additional analyses that I cannot discuss today, and they are referenced here in the orange box. So the 4B final state has the advantage of featuring the largest branching fraction with about 34%, and the search is conducted in for the non-resonant production in the resolved and boosted channels, targeting different production modes. And the boosted analysis is the first one to use the particle net algorithm to identify the BB bar merge jets versus standard model background, for example, TT bar. And the BB tau tau analysis is done in the resonant for the resonant and non-resonant production, targeting both of the gluon-gluon fusion and vector boson fusion production modes. And it features the best expected limit to date, profiting from a reasonable branching fraction and a rather low background. The vector boson fusion is quite important as it allows to assess the VVHH coupling here on the bottom right, as well as the VVH, in addition to the tri-Higgs coupling. And in the standard model, there are large cancellations between the tri-Higgs coupling and the box diagram, the two left diagrams, as well as the VVH and the VVH here, second from right, and VVHH diagrams. These cancellations are not present in some BSM theories, so there's quite a discriminating power. And also the tri-Higgs coupling is a critical input to the standard model as it tests the Higgs potential, and this has implications on the vacuum stability. On this slide, you see the results for the 4B analyses. So far, no evidence for signal is observed, and the searches are mostly limited by statistics. For the resolved analysis, you see the result here, where the limits above the pink theoretical prediction are still allowed. And this leads to the ranges of the kappa parameters you see here. And in terms of the standard model, assuming that this is what we are looking for, the gluon-gluon fusion production cross-section is constrained to be below 3.6 times the standard model prediction, which is a very, very low value already. For the vector boson fusion, this value is about 226 times the standard model prediction. In the boosted analysis, similar limits can be calculated. Again, the part above the red line is still allowed. And the observation here excludes a value of kappa 2V equaling 0 at 95% for all remaining allowed values of kappa V. And you can see limits in terms of both of these parameters here on the right-hand side, where the part between the bands is still allowed, and the red diamond is the standard model prediction. And the small dotted lines are respective vector boson fusion production cross-sections. So this brings me to my summary. I presented various analyses targeting Higgs physics within and beyond the standard model. So far, all results agree well with the standard model predictions within their uncertainty. However, there are additional exciting analyses to be published rather soon, especially lots of run-2 BSM results are still to come, and significant improvement in statistical precision is assumed to rise with the upcoming LHC run-3 and the high luminosity LHC. Thank you very much.
So the first question is, could you tell us the highlights of your talk in simple words, so because it will be an outreach.
Yeah, okay. I will try. So so far, people are looking at experiments in order to verify a certain theory, the standard model theory, and they're trying to investigate how certain collision reactions are verifying or falsifying this model. Now, this model is not the only option which is there. In principle, you can also have other descriptions of nature. So in my talk, I was trying to highlight and point to additional possibilities which could be there and ways to find them, or already given limits from current observations to find them. So I would say this is the highlight of my talk, and I'm especially always trying to have a lot of interaction with experimental colleagues, so that we are on the same page in terms of what can be found and investigated. I think this is quite important for our field.
The other point is, although you are only a few days here, I mean, what is your impression of what we are doing here? I mean, the people we bring and...
Yeah, I mean, I think it's very nice. So I heard about these Corfu workshops for a long time, and I always wanted to go. So your
you are here, then.
Outside commercial is very good. People say I want to come as well at some point, like me. Yeah, I like it a lot. I mean, it's also due to the fact I know some of the organizers quite well, so it's a nice reunion in a sense to meet people which are usually spread all around the world, or all around Europe in this case, to meet and also not to be too much distracted by other things. Yeah, so.
And also you see we have several young researchers.
Yeah.
So what will be your advice to them? I mean, our field is still interesting to attract people.
Sure.
They should
there's an infinite number of questions which need to be solved. I mean, I think the best advice one can give to anyone is to do what you find interesting, right? So this is the thing. And I also have to say, in the beginning, if you start studying, it's very hard. So it sometimes filters out a lot of people. It's sometimes even done on purpose, because afterwards it will not be easier. Yeah, but again, as you say in German, everyone is cooking only with water. So even if things are looking extremely difficult in the beginning, in the end, if you're really interested, if you're interested in this and you try to understand it, you will. And you will also find some people who help you with this. But you also have to work hard yourself, right? So it's not an easy topic. I mean, this should be clear to everyone. So I want to thank the organizers, they are somewhere, for inviting me after hearing so many good things about this meeting. Finally, I can be here, and so far it has been very nice. So as Werner said, I will talk about constraining extended scalar sectors at current and future colliders, and this is based on work with a large number of collaborators, which are listed here, some of them in the audience. So there are some introductory slides. I think I can go very quickly because most of these things have already been said in earlier talks today. So usually one says after the Higgs discovery in 2012, the last building block of the standard model has been discovered. What are the remaining questions? One can ask, why is the standard model the way it is? So search for underlying principles or symmetries. Find explanations for observations which are not described by the standard model. A prime example is dark matter, or one can try to explain the flavor structure. Or you can take an ad hoc approach and say, I want to test which other models will comply with current experimental and theoretical precision and constraints. Okay. The collider landscape, I think I can also go very quickly over this because I think you're all aware of these various options. So currently we have the LHC running as a future option, which has been already approved, is the Hailuri LHC. I right now 14 TeV. I hope this will happen. high luminosity, and then a future possible option is FCCHH. This is under discussion. Then we are at the plus minus colliders. We already heard a lot about this in one of the previous talks. Again, there are various options on the market, supposed to be high priority in Europe, with various center of mass energies which are discussed. And a recent revival, I think, have been mu plus mu minus colliders, which are currently hotly discussed in various forums, and we will see what comes out of this later on. Okay, what is the special role of the scalar sector? I mean, again, I think, more or less go through this because you all know it. So this is the Higgs potential in the standard model. The web basically causes masses for the Higgs boson, gauge boson couplings. Everything is determined in terms of gauge couplings V and lambda. And what is important here, I think, is that the form of the potential determines the minimum and the electroweak vacuum structure. Yeah. So, and this has important consequences, for example, for the stability of the universe, electroweak phase transition, and so on. So when one says we already know everything and we have seen everything in the standard model, it's not completely correct, because what we did not check yet are these couplings in the standard model. So triple Higgs and quartic Higgs couplings, they are predicted to have a specific value from the standard model alone, but we have not measured them yet. Yeah, we have constraints on this and projections of possible reaches for future colliders, but so far we don't know. So in a sense, we are not done, even with the standard model test, I would say. So then if you say, okay, let's go away from the standard model, what can I do now, concentrating on the scalar sector? In principle, you can do what you want. Of course, you have to have some sanity checks. So the first sanity check would be to have a suitable electroweak braking mechanism, including a Higgs candidate at 125 GeV that complies with current measurements. And also your additional scalars should not be excluded by current searches and precision observables. Now, nice add-ons could be, for example, that you can push the vacuum breakdown, which you have at a relatively low scale in the standard model to higher scales. I mean, this is the kind of, has been at least the kind of prominent feature of various models, or explain additional features like dark matter or hierarchies in the quark mass sector. Now, of course, there's a multitude of models out there, and if you're concentrating again on the scalar sector, what you can do is add as many as you want, gauge singlets, doublets, triplets, and so on, and this leads to new scalar states. So here's an example of the scalar sector for two Higgs doublet models. Okay, the very, very simplest model, just as a kind of warm up, is you have a singlet, a gauge singlet, real singlet, which you add the Z2 symmetry. This means you have one scalar particle. This is the potential. This is the standard model like equivalent, and the three additional terms are add-ons in this model. You have new parameters, so the mass of the second scalar, then a mixing angle, which would be 0 in the standard model, and the ratio of the wefts. So we assume this singlet to have a vacuum expectation value. Now on the left-hand side, you see a relatively updated plot now on the comparison of various bounds as a function of the mass of the second scalar between 200 GeV and 1 TeV. This is the sine alpha. So again, remember sine alpha equals 0 would be the standard model, and I compare various lines here. So for example, the pink line is the signal strength measurement. The green line are direct searches for heavy resonances. Then you have constraints from the W boson mass, and as an example, I also show perturbativity of lambda 1 coupling. And the way to read it is you go to your favorite mass, and then you go up until the first line you meet is the strongest constraint. And what is interesting here is that now, in fact, we already have strong constraints in large parts of parameter space now from direct searches. But then at some point, the W boson mass takes over. So I think this is an interesting thing, and one should remember electroweak precision is important as well, right? On the right-hand side, you see predictions for heavy resonance going to two standard model-like particles, so di-Higgs searches within this model. Yeah, you see a projection. I mean, this has not been updated, so this was the Atlas combination of early run to data, I think, but we haven't updated this yet to full results. And you see that in large regions of parameter space, due to current constraints, the model basically does not reach the limit. However, for lower masses, you also have constraints already from this within this model. Okay, so I show you the sensitivities in figures. Again, the lines are the cross sections you would need for 1000 events for the design luminosity. On the left, upper left, you see here as a function of the mass sum of the produced particles, the cross section in femtobarn, 2 different lines for now in Tailumi LHC for various production processes here. And you see that basically all of them follow this pattern of decay as the mass sum increases, which is due to only phase space being the important parameter here. Apart from this AA, there are slight differences because the couplings are different depending on the process. But apart from this AA, where really things are jumping up and down, and this is due to the fact that this depends really on this kind of slightly different coupling here. Okay, and you can see already, you can read off at Tailumi LHC, we would go in principle up to 1000 TV as a mass sum with this counting criterion. On the right-hand side, we do the same plot for various center of mass energies, now only for selected processes, 13 TV, 27, and 100. And you can again see that, especially for the 100 TV collider, I mean, this would be, in a sense, everything, or at least 1000 events would be produced. Again, this is without a detailed discussion. Yeah. Now then, on the lower left, we say what happens if we include the VBF type signature here. Things are getting more complicated because many more diagrams contribute. It's now only not this S-channel trail production, but you have a lot of different diagrams. And this leads to kind of interesting structures involving interferences and cancellations, which are not so easy to understand. Okay, thank you. Which are not so easy to understand, but you see, especially for this AA, which was kind of hopeless here, and we didn't even plot it here anymore. Now things are getting more interesting, and the reach really gets expanded, including this VBF type structures. And on the right-hand side, we played the same game for muon colliders. Yeah, and again, the structure here is not so clear, so you don't have this pure falling behavior. But on the other hand, it's possible at 30 TV, you're really basically covering nearly the whole mass range we were looking at. So this is the same in numbers. Again, high energy, I mean, after Tailumi LHC, basically you reach the sum of masses up to 1 TV, apart from the AA channel, which is much lower. And then you can go through your different collider options, and all others means now all channels apart from this AA channel, which is special. You're basically there with all other options apart from this AA. And then if you use AA only, maybe at the PP colliders, things work out nicely, especially at FCCHH. And if you include VBF type topologies, then you're doing even better. I have to say here for clicks, I added the numbers, but this was done on a very different level. So this is based on extremely detailed investigations, including everything, background signal, Beamstrahlung, and so on and so forth. So in a sense, I mean, I put it in the same table, but they have been derived on a very different level. Yeah. Okay, very briefly here, the last model I wanted to discuss, a favorite model by the LHC collaborations, so 2x-doublet model, a pseudoscalar, and then a dark matter candidate. I mean, this has been explored in great detail, and we already heard some results about it this morning. You have this scalar particle content, so this is the standard model like scalar, then the typical in blue, the typical 2x-doublet model at additional scalars, and then you have an additional pseudoscalar and the dark matter candidate and a very long list of parameters. I'm not going to go through. I mean, you have 12 free parameters basically. Again, the bounds, similar to what I discussed before, what is important now is that you also get bounds from B physics, of course, and like in the IDM, from dark matter constraints, so relic density direct detection, and I did a small pseudo recast from current LHC searches, and these are the codes which I used in addition to the ones I already mentioned in the introduction. Okay, and I'm already at my summary and outlook. So the LHC already constrains some models, especially It also does not constrain some other models because they are not investigated, which I think is not so good. Obviously the role of future colliders is equally important. And this picture I stole from Tim, where basically you can see that the BSM Higgs or scalar can connect to many, many important parts in theory and experimental space and techniques.
The first question is, could you tell us in simple words the highlights of your talk in a simple way, because it will be an hour.
Of course. First, let me say that the pleasure is all mine to be in Greece, for I don't know which time already, but the first time at this conference. So my talk was about future E plus C minus colliders as options for Higgs factories. I think that they are very attractive option because they are ready to go project. It means that if they are going to be approved, we can start building them immediately. And I try to argue in my talk why it is important to have these devices to address physics in the Higgs sector, and also implications from beyond the standard model physics in the Higgs measurements.
Very good. Something else that I would like to ask you is, although you have been only a few days here, you were the other day in the concert, you have seen what we do around, you have seen also the program, we have a boat trip, the Greek night, I hope you will dance there. And we also hope to construct very soon all these buildings so that next year you can provide office space for the participants. So just let us know for the audience what is your impression so far from what you are doing.
I really love to be in such a magnificent place. I mean, the nature, the surroundings is superb. It's the great effort of the organizers to have this event. And I think it is one of the only few events of this type in Greece. So, of course, I support it fully and enjoying being here.
Thank you very much. And the other point is that you have seen so many young people around who are starting their research in one way or the other. And what would be your advice to them? Is it worth trying? Is the effort?
Well, I think this is the very important time for physics. Maybe could be compared with the beginning of the 20th century, because we are hitting a sort of a wall with our disability to fully understand the nature of the space-time. We discovered Higgs boson as a unique particle that should be scrutinized through experimental and theoretical studies. And in a way, I'm happy to share this time of being active in physics with those young people.
Can I continue? Thank you. So, I mean, most of the people here are theorists, so probably I do not have to explain very much why do we need Higgs factories, but I will nevertheless introduce linear collider projects as a possible options, talking a bit on their detector concepts and technologies and what can be measured in the Higgs sector with these devices. Okay, because I'm experimentalist, I have naturally my favorite theorist, which is Nima Arkani Hamed, which I robbed by a few slides. As already said in the previous talk, Higgs discovery ended era of reductionism and symmetry in particle physics. So we observed a unique particle never seen before, fundamental scalar unique in itself couplings, that basically opened two important questions of the nature of the relativistic vacuum. How can we accommodate it in the observed density of the universe, and why Higgs is not enormously massive or even Planckian? This can be formulated as a well-known cosmological constant and hierarchy problem, where Nima is here asking even more liberally formulated question: why is there a macroscopic universe at all? At LHC, we do not have new discoveries, so basically there are only limits improving with every run. And with the current resolution, for instance, to probe Higgs compositeness, the Higgs could be as point-like as elementary as pion. Also, even high luminosity LHC could probe Higgs self-couplings with 50% uncertainty. So being a harbinger of the profound new principles at work in the quantum vacuum, Higgs should be studied more closely. What brings us to the Higgs factories? Higgs factories are prioritized in the European particle physics strategy from the last year as the highest priority future initiatives. There are several projects on the market, all offering millions of Higgs bosons. Some are linear. I'm going to focus on linear, ILC and click. Some are circular, CPC and FCCE. All electron-positron colliders comes with a set of advantages, like the initial defined initial state, which means reconstructible events from the first principles, also almost QCD-free environment. And what is a particular feature of a linear colliders is the accessibility of the high center of mass energies above TeV. This brings particular benefits when it comes to the measurement of the Higgs self-couplings and also BSM signatures in the Higgs sector. At E plus E minus machines, high precision measurements will be dominated by statistical uncertainty. It's clear that will be run for statistical precisions. The starting point is 100 times the lab luminosities. Of course, circular machines are in favor when it comes to luminosity, while a linear could address the higher center of mass scales. ILC is the oldest project, and I could proudly say that I was with the Tesla project, which was European project of the future linear collider already from 2000. Now it is merged from Japanese, American, and European project, where European Tesla technology developed at DAISY was adopted in 2004 by ICFA. This is a cold superconducting machine. It is staged. Basically, it can run from the Z0 pole and WW threshold for precision electroweak measurements up to where beam polarization is available up to 80% for electrons and 30% for positrons. The footprint for the first phase is 20.5 kilometers, and the site has already been chosen in Japan. It's Kitakami, where again with years of geological and similar surveys. I think the free electron laser, European free electron laser operating now as XFL at DAISY, is basically the largest ever accelerator prototype, where basically the full industrialization of the ILC-like cavities is demonstrated. This is a bit of history of the project, which is now in the phase that international development team is being built in order to prepare a laboratory in Japan. And as I said, it all depends on a political decision to build this machine. What is nice about ILC is that, like LHC, it comes with a set of auxiliary experiments, so which are non-collider experiments to study dark sector in the form of parasitic fixed target or beam dump experiments under the name of ILCX. Two detector options are being developed. One is ILD and the other is all silicon SID. ILD is mother of all detectors, because every future E plus E minus project would start from ILD and then modified according to its conditions. It is optimized for center of mass energy from the Z0 production up to 1 TeV, and the particle flow is the key word for all these detectors, because only neutral hadrons are left to less precise hadron colorimeters for determination. Everything else, of course, except for photons, which are detected in the eCal, comes in combination with the central tracker, leading to the jet resolutions between 3 to 4%, which is really needed to distinguish between Higgs W and Z jets. Another very interesting project, this is hibernated now at the moment by CERN, but unique in its feature to access 3 TeV center of mass energy is CLIC. Differently from ILC, it's a warmer machine, so normal conductivity, high current drive beam feeds the electromagnetic gradient to the main beam. And in the CLIC test facility at CERN, now operating, it's clear, the ability to reach 100 MeV, megavolts per meter gradients in the main beam cavities is been demonstrated. CLIC detector is again, as I said, started from ILD, but then the central tracker is replaced with silicon, so it's all silicon tracker. It's a bit more compact, again, heavily relying on particle flow calorimetry, with the timestamp readout, which is in case of CLIC and not of ILC, needed because of the beam-Strahlung interactions that are more pronounced in the higher center of mass energies. This project is also well documented in the yellow reports. This is a comparison what can be done in terms of Higgs couplings at T plus T minus colliders with the situation at LHC and PP in general, where I emphasize again the high energy benefits I'm going to talk now. Okay, you are all theorists, so I guess that I do not have to spend much time on this slide, how well we need to know Higgs couplings. So basically, electroweak couplings of electroweak bosons are particularly sensitive to BSM contributions, lambda even more, and apparently they have to be known at the percent level. And this can be achieved with already in the first phase of operation in the model-independent way. This is the example from CLIC, and this is the example from ILC, where we see that precision of Higgs couplings to electroweak bosons can be measured below 1% already in the first phase. The situation is similar also with circular colliders, and of course, everything is, these machines are superior in combination with high luminosity LHC. I think this is a clear demonstration of such a synergy of a future E plus E minus machine with high luminosity LHC, where already the first phase leads to a huge improvements of high luminosity LHC accuracies. Here, in the case of CLIC, where you add up all phases in combination with high luminosity LHC, practically most of the couplings can be measured at the Fermi level. Now we come to maybe the most critical measurement, and this is Higgs self-coupling measurement. The previous speaker also discussed it. And it is, of course, quite important to know lambda determining the shape of the Higgs potential, but also receiving eventual contribution from BSM models, or being significantly enhanced in the electroweak barrier genesis models and so on. WW fusion, where Higgs decays to a pair of Higgs, is apparently the most sensitive process, and it is clearly illustrated that sensitivity is rising with the center of mass energy. So it is no strange that CLIC actually could be superior by reaching 3 TeV in measuring the Higgs self-coupling below 10%. You see that high luminosity LHC cannot do more, or even high energy, because these measurements are constrained by theoretical uncertainties. Of course, everybody likes to compare everything between projects, linear versus circular, lepton versus proton, and so on. So I try to do a fair comparison here, which is again personal view. Precision-wise, linear circular colliders are comparable when it comes to the Higgs couplings. But due to the high energy excess of the high cross-section production mechanisms, you can measure rare decays at linear collider, you can superiorly measure Higgs self-coupling, and you have enhanced sensitivity to the BSM contributions in the Higgs sector. Great advantage, at the other hand, of the circular machines is the extensibility of the Higgs span. You can insert proton in the same tunnel and boost them to 100 TeV center of mass energies. When it comes to the prediction and future 100 TeV hadron collider, there are a few open issues at the moment, like the accelerator and detector technologies, the huge pileup, which will be of order of 1,000. So one really have to think how to reconstruct events under such experimental conditions, and the control of theoretical uncertainties. You all know this better than me, and I just like to point out that significant amount of work in theory is needed in order to improve PDFs, improve non-perturbative calculations, and so on, needed for instance, FCC HH at the level of 100. So you have to improve the 100 times the current theoretical uncertainties, which is quite demanding and presumably requires years of work on it. I'm coming to my summary. I hopefully convinced you that all future E+ E- projects bring significant added value to the projected high luminosity LHC sensitivities in the Higgs sector. The feature of E+ E- machines is our measurements in a model-independent way, where the highest center of mass energies bring added value in terms of the Higgs self-coupling measurements and sensitivity to the realization of BSM scenarios in the Higgs sector. I have basically two main messages. One is that upgrade is important, that these machines should not serve only at the first stages as Higgs factories. High center of mass energies are genuine advantages of a linear collider, and basically they are ready to wear projects if there would be a decision to have them. Thank you very much.
So this time we have with us Emmanuel Tsesmelis from CERN. So please, Emmanuel, tell us briefly or explain to us better the main subjects of your talk.
Yes, so my presentation this year in the Corfu Institute was focused on a future project, a future possible project at CERN, the Future Circular Collider, which is now undergoing a feasibility study for the next 5 years, leading up to the European Strategy for Particle Physics discussion and deliberation in about 6 years from now. So it was really focused on the current activities for future machine, which this future machine could start off as an electron-positron collider, as a Higgs factory and the electroweak factory. And then that same basic infrastructure, and particularly the tunnel, can then be used to host new high energy proton machine and ion machine, a hadron collider, following the electron positron machine, very similar to the model that we used for LEP and the LHC. Yes.
Okay. Your experience, your previous experience on the Corfu Summer Institute, and please tell us some words about the workshop that your talk was addressed to.
Yeah, indeed, I've been coming or participating in the Corfu Institute now for many years, actually 10 or more years, and I've always enjoyed the time I had, even though it was a short time, to be on the island itself, which is a beautiful island. I think everyone agrees to that. And the workshop itself has developed into one of the landmark, let's say, appointments on the calendar during the summer period. And I think I've seen it develop very positively in these intervening 10 years. And for me personally, it's been always a pleasure to give a talk on what's happening on the accelerator side, accelerator projects at CERN, which actually set some direction in the future of the field in Europe and internationally, of course. It's always great to meet with people there. Because of COVID, of course, this has been more restrictive in a couple of years, but I hope to be back on the island and in person at the Institute in 2022, and also meet with people there. Professor Zupanos, who's been a stalwart and the centerpiece of this institute from its inception. And I'd just like to thank him personally also for making it such a success, and also for inviting me on a regular basis to participate, which is always a delight and pleasure for me to do so.
Okay, and some words to young students starting research.
Okay, so actually this is a very, very excellent moment to get into research in particle physics. There's of course the LHC at CERN, there's the neutrino program at CERN is participating in programs in the US and Japan. There's many projects on the table as well for the future, whether it's a linear collider or a circular collider. This is a fantastic moment to enter the field. Especially the future projects, of course, need the young people. Obviously, we're looking at a program which is going to be decades into the future when you look at a linear collider or a future circular collider. And that's where we need the young people to get involved. And one of the aims of our team in the future circular collider in particular that I know is that we are reaching out to the next generation of scientists and engineers who are going to develop these new machines, operate them, and do the physics of them up to the end of the century. So we really depend on the next generation of young scientists and, very importantly, engineers to make all that happen. In addition, of course, to the current exciting physics programs at the LHC, and very soon at its high luminosity phase, the high luminosity LHC. So a fantastic moment to get involved, guys, and into the field. Okay,
thank you very much, and we hope next year we'll all meet physically in Corfu. Thank you very much.
I second that. Thank you very much.
Thank you. Bye-bye.
Indeed, it's a pleasure to be with you, even though I cannot be there in person on this particular occasion. But I'm happy to report on the Future Circular Collider and also the feasibility study in particular, which has been launched recently in terms of that project. So what I want to refer to is, is the fact that we've had, as many of you know and participated actually, is the, can someone please mute? Someone has their mic open, I can hear an echo. Can everyone? Yeah, that's better, thank you. Yeah. Okay. So this actually refers to the update of. No, that's not good. I think everyone has to mute, otherwise I'll get an echo. Hello? Yeah. Okay, that's better. Thank you. What I was referring to is the scientific priorities for CERN for the future are actually set out in the update of the European Strategy for Particle Physics, which was updated just over a year ago now in June 2020. And of course, part of that European strategy, which develops a roadmap for European particle physics well into the future, is of course the LHC and its high luminosity upgrade. And those two elements are now in either in operation mode or in preparation mode. From the mid-2020s, we will also have the high luminosity LHC, and there has been a dedicated presentation on that in this workshop. But looking further ahead, the European strategy has underlined the importance of a Higgs factory for the further understanding of the Higgs boson itself. And that could be done by various means, either in a circular collider mode, of which the FCC is a prime candidate for such a facility, or a linear collider mode. And that's where we have the International Linear Collider and CLIC offering the two possibilities for that sort of scheme. In addition, and in parallel, I would say, the European strategy has set forth a program of investigation for the technical and financial feasibility of a future high energy frontier machine in a 100-kilometer collider at CERN. And I'll be focusing both on that longer term machine, Hadron machine, and also on the Higgs factory related to the FCC in this presentation. All these future projects, of course, need R&D, accelerator R&D, and also detector R&D. And although I don't have much time to talk about that, there is in progress now both an accelerator R&D roadmap and a detector R&D roadmap process, which is going to be delivered to the CERN Council towards the end of this year, which actually implements or sets out a roadmap for implementation of the strategy of the European Strategy of Particle Physics of last year. So that's in progress. So what I'll be talking about in this presentation is this future circular collider, which you can see there in relation to the LHC hosted by CERN in the Geneva area, straddling, of course, the French and Swiss border in the region of Geneva. So, so what is this? The Future Circular Collider itself, the study was launched, the phase 1 of that study was launched in 2014, and it underlined an international FCC collaboration to host at CERN a new facility, a research infrastructure, a unique facility in the world based on a proton-proton machine, which is called the FCC-HH, which actually will define the infrastructure requirements for such a facility, based around a tunnel, which will be somewhere in the range between 80 and 100 kilometers in circumference. And this will define the infrastructure in the Geneva area. This Hadron machine, the R&D, as I'll come back to later, is very much focused on the requirements of high field magnets, superconducting magnets, reaching up to 16 Tesla in magnetic field to be able to reach 100 TeV proton-proton collisions at the center of mass energies. As a first step, and leading towards this future Hadron-Hadron Collider will be an E+ E- collider, the FCC-EE, which will be for the purposes of a Higgs factory and electroweak factory for that matter. In addition, as part of this study, this phase 1 study, there was the option of a proton-electron collider, the FCC-HE option, which was studied, and also perhaps a high-energy LHC machine, which will be the LHC housing center of mass energies up to about 27 TeV with the 16 Tesla superconducting magnets foreseen for the PP collider for the FCC. So that is the reference, which was set out already about 7 years ago in 2014, and I will discuss what's happened in the intervening period. So the FCC program itself is inspired by the very successful LEP and LHC programs at CERN, and this tandem of operating a lepton machine and a hadron machine has served the particle physics community very well, and also serves CERN very well. And indeed, in terms of the FCC, this foresees a comprehensive and cost-effective program maximizing the physics opportunities based on the stage 1 FCC-EE, which will be the study of the Higgs boson itself, the discovered Higgs boson, and perhaps others to come in the electroweak and the top factory at the highest luminosities. So this is effectively a Higgs and electroweak factory of study. Followed by stage 2, hadron-hadron machine at a top colliding energy of 100 TeV as a natural continuation of the energy frontier, with also the ion and electron hadron options in the background. So this actually involves a complementary physics. It involves a common civil engineering, which is very useful, and common technical infrastructures, at least for the most part. And we are building on and reusing not only CERN's existing technical infrastructure, but also the expertise available in the lab, which has been developed over many decades. And looking forward to the subsequent hadron-hadron option, the advantage here is, of course, the tremendously high integrated luminosity, which can be gathered in about 20 years of operation at record energies of 100 TeV. This estimate of 30 inverse attobands is about a factor of 10 more than what will accumulate in the LHC and high luminosity LHC option. So, and of course, this translates into a very high production rate of the known particles, the known Higgs particles and electroweak particles, but also allows to perform high precision studies of the Higgs and top, and sensitivity to heavy new physics, all the way up to several tens of TeV, depending on the particle you're looking for, whether that's new gauge bosons or new particles of dark matter, which can reach up to several TeV in reach. So new windows, new vistas open, both in terms of the statistics and precision offered by the FCC-EE, and also the precision and mass range available to a new FCC-HH machine. So these are very important and very key underlying physics motivation themes, which motivate the machine FCC-EE and FCC-HH. So moving on, you can see there is now a launched worldwide FCC niobium 310 program, where we do not depend on niobium titanium as we have done for the FCC, which has enabled us to run the LHC at 8.3 Tesla. We will be operating at 16 Tesla, and hence we require a new type of conductor. And this conductor, the main development goal is to develop a conductor performance increase of about 50% relative to the high luminosity LHC. And we need the current density of about 1500 amperes per square millimeter, which will enable us to increase the density, the current density, which will enable us to reduce also the size of these dipole magnets. So indeed, over the past few years, we are working together, not only with universities and institutes, but also with industry. As you can see here, this is a worldwide collaboration, which will enable us to develop the new type of conductor based on niobium 310, which already shows very nice results, going out to about 15 Tesla also. And I show you one very nice example. Well, first of all, I show you the 16 Tesla design activities and options. These are 5 different types of magnets, which are developed by 4 different universities or institutes around the world. And we are to build, based on these designs, short model magnets of about 1.5 meters in length by the mid-2020s. That's one of the challenges which has been launched as part of this feasibility study of the FCC. And in this work is being done in Europe mostly. However, on the other side of the Atlantic, there is a very important US magnet development program, which is underway, particularly at LBNL and also at Fermilab, which are developing the same type of R&D programs for high field magnets. And indeed, the US Magnet Development Program has produced a short model, as you can see there, about 1.5 to 2 meters, which actually reached 14.5 Tesla based on the new conductor of niobium 3 tin. And this is, you can see here, the Bohr field as a function of the quench number. After a certain number of trainings, of quenches, they reached 14.5 at 1.9 Kelvin, which is the superfluid helium temperatures offered. So that's a fantastic achievement, and this bodes very well for the development of these magnets for the future. So this is the first FCC integrated project technical schedule, which has been produced. Year 1 here is basically 2021, where we are today. And you can see it extends over 70 years in total. There will be 15 years of operation of the FCC EE machine and 25 years of operation of the FCC HH machine. And the initial period, the coming 18 years, will consist of taking care of all the administrative procedures, both for Switzerland and France. Although 3/4 of the machine will be located on French territory, 1/4 will be on Swiss territory, and doing, of course, all the preparatory studies and work for the civil engineering and actually carrying out the civil engineering itself, and then followed by the FCCEE machine construction and installation and commissioning, and in parallel developing the systems required for the Hadron machine, which will be installed following the construction, the termination of the electron-positron program. So this gives you the overall timelines. The initial period consists of engineering design, energy efficiency, and maintainability. And then we go into the conductors and high field magnet technology required for the Hadron option. So overall, it's an integrated project for 70 years. And if I look back perhaps to the case of LEP/LHC/high luminosity LHC, in terms of years, it's very similar, I would say, in terms of overall years from the early 1980s to the year 2040. It's a little bit longer, but very similar timescales. So all this, the feasibility study has to report by the time of the next European strategy process, which will be around 2026 or 2027. But as I'll show in a moment, there's quite a few steps to reach that. So this shows a little bit more detail, and this is where support and help is solicited from the worldwide particle physics community. In terms of what has been set up is actually 6 working groups. One is physics experiments and detectors, the other one is accelerators, the other one is technical infrastructure, and then organization and funding, and civil engineering and host state processes. This study support and coordination runs through horizontally these other five work packages. So these are the areas which we have to deliver, and this is the timeline which we have to do this, starting from mid-2021. In fact, the feasibility study was launched at the FCC week in June of this year, and the end point is with the delivery of a feasibility study report, which would update the CDRs I mentioned earlier and provide a more technical appraisal and a more technical design of the concepts presented in the CDRs. And at that point, we should be addressing, of course, very substantially the technical and financial feasibility of building such a machine. And of course, this will feed into the next European strategy towards the middle to end of this decade, at which time we would hope a decision will be made on the future of such a machine of the FCC, and a decision by the European strategy, which will then obviously take in international partners. A formidable challenge, of course, is the detector itself. And here I show you the challenges for the Hadron Collider. The requirements are well beyond those for the high luminosity LHC, and this will be revisited through this feasibility study. So this is requirements there have to do with a much larger longitudinal event boost at the much higher collision beam energies that we have. We have very high, the produced particles will be very highly boosted because of, especially in the high PT final states. We have perhaps up to 1,000 pileup events per crossing, very much higher compared to the LHC and even compared to the high luminosity LHC. We have energetic jets, we have high PT muons, and we have the requirements of significant radiation harness requirements for the electronics, which will be, and the sensors, which will be in the detector. So all this is being carried out as part of a program of what is called PED, which is the Physics Experiment and Detector program of R&D and coordination, which will brings together those three pillars: physics, the experiments, and the detectors, to design this the detectors for the both the Lepton Collider and the Hadron Collider. So, in conclusion, we have completed the first phase of the FCC design study particularly through the Eurocircle support that we have. We have baseline machine designs, performance matching the physics requirements at the time, and this has been documented in 4 CDRs. There is an integrated FCC program which was submitted to the European strategy update, which was updated in June 2020. And the request for the feasibility study as a basis for the project decision later this decade was approved. And actually this feasibility study has been launched, and we're in the process of working through the requirements until later this decade to be able to deliver to the European strategy a feasibility report on how well that such a facility can be actually built technically and financially in the Geneva area. And in the longer term, following obviously approval, going through the approval processes which are required, the longer term goal is, of course, to build a world-leading high energy physics infrastructure for the 21st century to push the particle physics precision and energy frontiers far beyond the present limits of the LHC and the high luminosity LHC. And just like to finish by saying that the FCC collaboration is an open collaboration, and we are welcoming new participants and new contributors to this feasibility study phase and to the FCC innovation study phase project that's also been launched for the coming years. And with that, I'd like to thank you for your attention, and I'd like to end there. Thank you very much.